One of the special types of equilibrium that we were looking at dealt with acids and bases, and especially a very important acid-base equilibrium which we refer to as buffers. As I indicated in the previous lecture, many of our chemical processes, our biochemical processes, require a very specific pH to properly function. And so we have a lot of different buffers within our own human biology. Buffers are very important in industry. Oftentimes to prepare a product requires a very specific pH or pH range. And we said that buffers were chemicals then that have a relatively constant pH. Even if we add some acid or base to that solution, that buffered solution, the pH doesn't change any appreciable amount. And once again, as we pointed out in the previous lecture, buffers are made up of then either a weak acid and its conjugate base, meaning the anion of the acid. And as an example here we had cyanic acid and the cyanide ion. And of course, when we write the cyanide ion, and maybe I should have pointed that out previously, we can't just dump in cyanide ions into a solution. We always have to put things in as compounds. So there will be some other positive ion that goes in, but it will be an ionic compound. So when you put it into water, it dissolves, it ionizes, and so it's really the cyanide ion that we're talking about. For instance, we might put it in like sodium cyanide or potassium cyanide. But the potassium ion or the sodium ion is not involved in the acid-base chemistry. Only the anion and its weak acid. The other type of buffer involves a weak base, like ammonia, and its conjugate acid, like the ammonium ion. Once again, even there, we can't dump in ammonium ions. We have to dump in an ammonium compound, like ammonium nitrate or ammonium chloride, something like that. That will give us a source of the NH4 plus ions. All right, so oftentimes we write only the reacting species. We talked about that earlier in the course. We talked about net chemical reactions, net ionic chemical equations, for instance, which show only those things that are really undergoing a change. And so that's the way we look at it from the standpoint of buffers. One of the other buffers that you may encounter, or certainly you've heard commercials about, is a chemical which is a buffered aspirin, specifically called Bufferin. And it is supposed to then be adjusted such that it doesn't upset your stomach when you take it. Actually, if one looks at it, it'd be very questionable of whether or not it has a whole lot of validity when one considers the stomach acid to be about a tenth to a hundredth molar hydrochloric acid. That's pretty strong acid. And the fact that you have a little tiny aspirin pill which has a small amount of chemical buffer with it, it probably is going to be zapped almost immediately by the acid in the stomach anyway. Now it may be buffered when you put it into a glass of water, and it might maintain a fairly constant pH there, but I really don't think that it's going to have a whole lot of buffering effect when we dump it into a 25 milliliters of stomach acid. So I think the buffering effect, it's good from the PR standpoint. It sounds good. It's a good advertising choice. However, I'm not sure that it has that much effect in terms of true acid-base chemistry. There are other chemicals, however, drugs, etc., that are buffered, and oftentimes those that are used externally, where we need to make sure that we maintain either slightly acidic or basic medium so it doesn't cause harm to tissue. For instance, eye drops may well be buffered so that we don't change the pH, so we don't affect the acidity in the eye and cause any damage to the tissue. So there's some real valid buffers in terms of medical application. But again, as I say, buffers are extremely important in both our biological system and in commercial production processes. We were beginning to look at a specific example and quantitative calculation involving a buffer, and the question that we had started to look at was calculate the hydronium ion and the pH of a solution which is made up of 0.76 molar chlorous acid, hypochlorous acid, and 1.56 molar sodium hypochlorite. Again, I pointed out there that this is actually, when we put it into water, sodium ions and hypochlorite ions. So the hypochlorite ion is the conjugate base, and the hypochlorous acid is the weak acid in this case. So we have prepared, or we have a solution then that fits under the category of buffer. We know what the acid dissociation constant is for hypochlorous acid, 3.0 times 10 to the minus 7. And we want to calculate the hydronium ion, so obviously to calculate the hydronium ion we needed a chemical equation. And we started out then by writing the chemical reaction for this process of the hypochlorous acid reacting with liquid water to give us hydronium and the hypochlorite ion. So here we see is the acid part of the buffer, and here is the conjugate base of the buffer. So we have our acid and the base necessary to produce then a buffer system. Initially, then we ask the question, how much of each of the species do we have in the system? We did the same thing when we talked about just a weak acid reaction or a weak base reaction, or when we talked about solubility. We said, how much of each do we have initially? And then we let the reaction occur and we say, now how much do we have when equilibrium, indicated by the double arrow, how much do we have when the equilibrium is finally reached? Well, initially in this system, we have 0.76 moles per liter of the acid, and we have 1.56 moles per liter of the hypochlorite ion. Now, we notice that the hydronium ion is 0. There hasn't been any, there hasn't any formed unless some of this reacts with water. So it starts out at 0. So then we said, all right, as we did with the weak acid equilibrium we looked at previously, we said let X, an unknown amount, let X equal the moles per liter of the acid that reacts with the water. And we're going to let it then reach equilibrium. In other words, X reacts, we finally reach equilibrium. We then ask the question, all right, once equilibrium is reached, what is the amount of each of the 3 species in the system? Well, quite obviously, or it seems somewhat obvious at least, if X is the amount that reacted, then the amount that we have left at equilibrium is what we started with minus the amount that reacted. And the only source of hydronium ion is the amount of acid that reacted, so its concentration is X. We already had 1.56 moles per liter of this species. If we form any hydronium ion, we must also form an equal amount of hypochlorite. So that's going to be in addition to what was there initially. So we have 1.56 plus X. Well, at this point then, we're now ready to go ahead, plug it into an equilibrium expression. As long as we have an equilibrium, we can write an equilibrium expression. We know what the equilibrium constant value is, and the only thing we're not going to know is X. That's going to be our unknown. We only have one unknown in the problem, and that is X. So let's go ahead then and write then the equilibrium expression. Ka is equal to the hydronium ion concentration times the hypochlorite ion concentration, all divided by the concentration of the hypochlorous acid. Now keep in mind, these are not the initial concentration. When we talk about K, we're already talking about the system has reached equilibrium. So, therefore, these are the equilibrium concentrations, which is this line right here that we just talked about. So we can plug in for the hydronium ion X. For the hypochlorite ion, we would now have 1.56 plus X. And for the acid, we're going to have 0.76 minus X. Notice we still have only the one unknown in the equation, which is X. And this is all equal to 3.0 times 10 to the minus 8. That was given to us up here at the start of the problem. All right, so now all we have to do is mathematically solve for X. If we were to go about doing this in full, of course, obviously we can see that we would end up with an X squared term again, because this X times this is going to give us an X squared term. So we're going to have an X squared term, an X term, and a number, and once again we would be faced doing a quadratic equation to get an exact solution for the problem. But as we did in the previous acid and base equilibrium, we said, let's see if we can make an assumption first. Let's see if we can solve for an approximate answer and not have to do the quadratic equation. So what we're going to do then is we're going to now look at this equation, and we're going to say we think that this plus X and this minus X are both relatively small as compared to the numbers that they're either added to or subtracted from. We expect it to be rather small, all right? And if that's the case, then we can initially disregard these additive and subtractive terms. Well, if we do that, you see, if we get rid of this and this, the only thing we have left in there is just an X. That's it, X and some numbers to work with. We don't even need to do a square root this time like we did in the previous problems. So rearranging this now, I'm going to have X is equal to 3.0 times 10 to the minus 8. I'm going to multiply both sides by that number, times 0.76. Of course, when I multiply this side by that number, it cancels out. Okay? And then I'm going to divide both sides by the 1.56. When I divide this side by 1.56, of course, it cancels out. And we're now left with the bottom expression for X. And if we now solve for this numerically, we would then end up with 3 exponential minus 8 times 0.76 divided by 1.56. And we have a concentration of 1.5 times 10 to the minus 8. Okay? Now, let's look just above where we worked here, and we see that X was equal to the hydronium ion concentration. That's how we defined the system, so that actually X is the hydronium ion. And so this means that this here, this number is equal to H3O plus. So we've now answered the first step of the problem. Let's slide the problem back down here for a second. Calculate the hydronium ion. We've done that. We've calculated the hydronium ion. And so once we know the hydronium ion, of course, we can go the next step, simple acid-base calculation for pH. And so pH now is equal to minus the log of 1.5 times 10 to the negative 8. Plugging that into our calculator then, we end up with a pH of 7.84. Now notice that the pH here is on which side, acid or base side? It's on the basic side, isn't it? Because neutral is 7. Anything greater than 7 is a base. Well, you see, that's kind of interesting when we think about it from the standpoint, how did we make this solution up? We made it up from an acid and its conjugate base, and yet it gives us a solution that has a buffer pH on the basic side. Well, that is very possible when we're adding an acid and a base, because in this particular case, because we have a fairly large amount of the base species, actually the equilibrium is going to tend, Le Chatelier's principle from chapter 11, the equilibrium is going to tend to stay even further to the left, meaning that this becomes even a weaker acid than it would if we just put it into water. And so, therefore, we can have a base buffer involving acids. Okay? All right. Any questions on the calculations involved in this process? Again, initially it might look kind of complicated, but dissect the problem, take it apart, and you know what information you have. If it's involving an acid, write down an acid chemical equation. And from that then you can start looking, what information do I have? I have a K. So if I have a K, obviously if I write an expression, I have a numeric value to begin to work from. Okay? Any question on any step there? All right. One of the interesting equilibriums involved in our biological system is how our body transports oxygen. This is talked about a little bit at the end of the chapter, but I want to spend just a couple of moments talking about it here in class this morning as well. This is the oxygen-containing or oxygen-carrying part of the red blood cell. This is what we call the heme. This is the heme structure. And then around it is a protein structure, a globulin it's called. So we have hemoglobulin, hemoglobin, however you want to pronounce it. But this is the structure. And this here actually is an Fe2+. It's not an iron atom, it's actually an iron ion. And it's that iron plus 2 in that heme structure that allows it to attract an oxygen molecule, have the oxygen molecule actually be stuck to, by charge and electron sharing, stuck to the iron, transported then to the cells in the body where an equilibrium begins to take place. We'll take a look at the equilibrium in just a moment. One other important aspect of the structure of the heme is the two carboxylic acid groups. Notice that this would have the general structure here. I'll draw it over here. This would be our C double bond O dash OH. That's the functional group for an organic acid, if you recall. And there are two of those on there. The importance of these two is that the presence of these acid species makes this molecule now be able to be polar in nature. Because it's polar in nature, it now makes it water soluble. Where most of the rest of the organic structure and the globulin part would really be water insoluble. And the red blood cell then would not be able to be carried, it would just settle out, rather than being soluble in the water, which is, of course, the major component of the blood. But it's these two sites now that account for the water solubility of the red blood cell. Now, let's look a little bit at the chemistry, the equilibrium involved in the process. This is the equilibrium that takes place in our body. We have the hemoglobulin, which contains the iron 2, and it's aqueous, it's dissolved. As it passes through the lung, it is exposed to dissolved oxygen. We breathe in air, 20% oxygen, and the oxygen, some of the oxygen is soluble in water. We have a small amount of oxygen dissolved in water. Obviously we do, because aquatic life can live, fish, etc., extract this dissolved oxygen by the use of their gills, and the gills on the fish really are acting somewhat like the lungs in our body. In other words, that when they're exposed to the water with the oxygen can dissolve out of the water into the blood in the gill area and then be transported to the fish. So when we breathe in, when the blood passes now through the very fine capillaries in the lung, the oxygen then, which is dissolved into the blood fluid itself, now can react with this heme part and form the oxygenated hemoglobin. Now, I've specifically colored these blue and red because the blood that returns to the heart, the venous blood that returns back to the heart, is oxygen deficient, and veins are typically blue looking in color. The oxygenated blood, the blood that's going in the arteries, is a fairly red looking color. This color change is due to the absorption of the oxygen. So the blood going away from the heart now is red in color because it is oxygenated. Okay? Well, we notice this equilibrium, and that's the important part. I breathe in, some blood passes through the lung. It's converted to the oxygenated form, passes through the heart, it's pumped to the tissue. Now, when it gets to the tissue where activities have been going on, say the muscle area, and activities have been going on that have used up the oxygen, then we will have a decrease in this in the cells. Now, remember Le Chatelier's principle. Le Chatelier's principle says that if I subject a system at equilibrium to a change, the system will try to correct for it. So if this oxygen that was in the cell is used up, that means it's decreased, and that means that this equilibrium is shifted in this direction, which means that this oxygenated hemoglobin now releases the oxygen back to the solution, and the oxygen is now available for whatever biochemical process it's going to be involved in, whether it's conversion of carbohydrates to CO2 and water and energy, or whatever other function it's carrying on at that point. But it's this constant shifting back and forth. When it gets to the lung, when this here, the deoxygenated blood gets to the lung, we have a high level now of oxygen as compared to the cells that it just left. And what is that going to do? It's going to shift the equilibrium back in that direction, and the blood is converted back once again to the oxygenated form. Okay? All right. Now, we have to have a certain amount of hemoglobin to carry a proper amount of oxygen to function well. And of course, the hemoglobin contains the iron, and so we must have some iron in our diet. And people that don't have proper amounts of iron, or body doesn't process that iron properly to make then the heme part for the red blood cells, we call that kind of individual anemic. Anemia is a lack of the number of red blood cells necessary to carry sufficient oxygen for the person then to function properly. And somebody that is anemic or has anemia, of course, is going to get tired much quicker. They can't get the oxygen to the muscles etc., fast enough so they are going to tire more readily. They're not going to have it be as active in general, so anemia can be a problem. And we can increase then the iron in the diet, and that sometimes will help. If that fails, sometimes in extreme cases of anemia, we actually have to go in and put red blood cells in. We do a blood transfusion. So we actually go in and just dump in some new, freshly prepared from a donor, red blood cells that can work. And oftentimes then these slowly are sloughed back off, and a severe anemic individual may have to have a blood transfusion once every week or month or so to bring their level back up. Now oftentimes if you have severe anemia, which can be caused also by sickness, then what we have to do is rather than attacking this part, we can attack that part. And one of the things we talked about, remember, oxygen is the number 3 industrial chemical, we mentioned that, and one of the uses of oxygen is in the medicinal end for oxygen tents, etc., in the hospital. You see, if again we increase this by giving the person 100% oxygen in their lung instead of 20%, even if we have low levels of this, we're still going to shift the equilibrium and end up with a fairly high level of oxygenated ones. In other words, at any time in our body, probably only a very small percent of the red blood cells are fully oxygenated. So if we can shift the equilibrium, even if we don't have a whole lot of the red blood cells, if we can shift the equilibrium, we can change the percent that are actually carrying oxygen and offset the problem of the anemia. So that's another possibility. Now, one interesting thing of one way that this automatically is adjusted in our body, people that live at high elevations, for instance, will have a much higher level of hemoglobin than people that live at sea level. The body is already compensated for the fact that if you live at a higher elevation, you breathe in less oxygen per breath than you do at sea level. The percent's the same, but the gas pressure decreases as you go up, and so the number of moles of oxygen you actually breathe in is less as you go to a higher elevation. If you're flying in a high aircraft, a high altitude aircraft, you better have an additional supply of oxygen or you're not going to function very well. So people that live at high elevations will typically have a much higher hemoglobin level than people that live at sea level. Now, one of the ways that sports people take advantage of this known shift in equilibrium, if you're going to train for the Olympics, where do most countries, think just specifically about the American athletes for the moment, but where do the American athletes train for the Olympics? Where? Colorado. They train at 6,000, 7,000, 8,000 foot elevation. Why are they training out there? Because they want to be out there where the air is thin and the sky is blue and they see mountains? No. They're training out there because with the less oxygen, their body, given about 5 to 7 days, is going to increase the amount of hemoglobin. The number of red blood cells is going to increase. Now, if I train out there and then I take off and I go to the event, the Olympic event, a few days before the event, it takes about a week for the body to go back the other direction. So now I've got more red blood cells available than I would normally have had I trained at a lower elevation. Well, what does that mean? I can carry more oxygen per unit of time than I could with less red blood cells. Now, there's nothing wrong with that. I mean, we're using an understanding of our biochemical equilibrium, and that's a natural process, and so there is nothing illegal about that. But there is some concern about something that is happening in sports that is somewhat not illegal, but maybe ethically questionable. One can donate your own blood. You can donate it to a collector who can spin it down and collect the red blood cells and store it. It's your blood. It's not unnatural to your body. It's not a drug. And so now, just before the event, reasonable time, half a day or a day, I go back and I have them give me a transfusion now of my own blood. So they've taken my own red blood cells, and of course once we give some up, our body replaces them. Okay, so when you donate blood, it only takes a couple of days and you're back to the same level. The body reproduces this red blood cell. So now I'm back to my normal, and I now take a pint of red blood cells that are my own, that I've donated, and I put them back in. Well, that, of course, greatly increases the concentration of red blood cells in our system. It's going to take, again, a couple of days for the body to slough off the excess. So I've got extra red blood cells. I go out and do my event. I can carry more oxygen. And does this give me an unfair advantage? Well, it gives you an advantage. There's no doubt about it. The question is, it hasn't been outlawed from the standpoint that the Olympic Committee only outlaws those things that are not natural to the body. And of course, if it's your own red blood cells, it's pretty difficult to say that this is not something that naturally belongs to your body. But it is something that is being looked at. And it may come down to the point of being then at least stated as an ethical concern, if nothing else. You see, it's a little hard to track. I mean, how do you test somebody for the fact that they've got their own red blood cells back? You can't. I mean, it's their own DNA, it's their own whole body system, and unless somebody says, yes, I gave that person a pint of their own red blood cells, there's no way that they could prove it. So it's not like a drug where they can test. This is something that is strictly an ethical question. A question back there.
Wouldn't it elevate their red blood cells?
Yes, that's exactly what they want to do.
Did they test for that?
Well, I mean, how do they know what the baseline is unless they're going to test every athlete for a baseline red blood cell count 2 days before competition and then in day of competition? They could do it, but that's an awful lot of testing to do. So, okay. All right. Now, one other thing that comes up is carbon monoxide poisoning, and this is an alteration of the equilibrium that normally occurs. Normally when you breathe in, of course, the oxygen goes to the hemoglobin. But if you breathe in carbon monoxide, the carbon monoxide will knock the oxygen off and form a carbon monoxide hemoglobin structure. That means that the oxygen never gets carried away from the lung. Because this equilibrium constant, the formation constant for the hemoglobin carbon monoxide, is considerably greater than the equilibrium for the formation of the oxygenated hemoglobin. So if I have any carbon monoxide in my lung, preferentially the red blood cell will take it and carry it rather than the oxygen. And of course, if you're slowly breathing a constant level of carbon monoxide, it doesn't have to be a very high level, but if you're constantly breathing that CO, finally you reach the point that you have so many of the red blood cells covered with carbon monoxide, you're going to become oxygen deficient, become faint, pass out, and of course, unless something happens to remove the carbon monoxide, one could result in death. This is a thing that you probably have heard considerable about in the last couple of years as far as home protection. For many, many years we've talked about smoke detectors in the home so that we have an early alert if a fire starts, because most people die not from the heat and burns, but most people die from the smoke. So if we have a smoke detector to warn us, then hopefully we can escape from the building in time. But also there's a concern that this no odor, no visible killer gas can also be in our home, carbon monoxide. And this is especially true in areas that have long winters, homes that are tightly sealed up because people want to cut down on heat loss. And if they have a furnace or a supplementary heater in the home that isn't operating correctly, then we might be producing carbon monoxide. And so they've now come out with commercial carbon monoxide detectors that look quite similar to smoke detectors that can be placed in your home, so that in case carbon monoxide does begin to be formed by your furnace or some other heating system in your home, the detector would warn you in advance. This is a silent, odorless killer. Smoke at least would tend to gag you and get you coughing, and that might wake you up in time to get you out. But carbon monoxide isn't going to do anything. It's just going to slowly build up, and before you would know it, it would be too late. Okay? Now, one other thing that interferes with our red blood cells, and especially in infants, are nitrites. Nitrites or nitrates, but usually it's nitrites that are used in foods. Nitrites are used in food to prevent them from decaying. For instance, red meat. Red meat is treated with nitrates so it keeps its red color. Okay? We tend not to like meat that looks brownish, but actually the meat that's brownish is probably better than the red meat. But it's just the appearance to us that we think that a nice, fresh-looking red chunk of meat is better for us than one that has some brown coloration. The brown coloration is due to oxygen reacting with the protein in the meat. Nitrite interferes, it takes that oxygen from the air and keeps the meat then from changing color. A lot of nitrite is used in bacon, red meats, and also in salads to some extent where we don't want a browning effect to occur. So if we cut up a large bowl of salad in a restaurant and we're going to have it setting out for a couple of hours, then we don't want it turning brown because that's not appealing to people. And so it'll be treated with a small amount of nitrite. Now, for most of us, it's not a real problem, but the nitrite will be converted to nitrate in our body. The nitrate reacts with the heme, and that's the iron 2, to convert it to a heme, but the iron now is a +3. Our next chapter, we're going to talk about oxidation reduction processes. This is an oxidation process that is occurring, iron going from the 2 to the +3. And iron in the +3 state, even though the whole rest of the blood cell looks the same, that iron +3 can't carry oxygen. And so therefore all of a sudden we have a whole bunch of heme now that can't carry oxygen. Now, as I say, this sometimes is very important in very young children. If their food happens to be contaminated with some nitrites, they end up with this. And of course, if you don't have oxygen-containing or oxygen-carrying red blood cells, you're going to end up with a venous color to you. And sometimes we talk about a blue baby, and a blue baby often is either that they have been given some nitrites accidentally, or that the body, there are other biochemical processes that can cause this, the body has converted the iron in the red blood cell to iron 3, and the red blood then isn't existent. So basically all the blood in the body now is essentially the same as venous blood. In other words, it's oxygen deficient. Okay? All right. Well, one last thing here I want to talk a little bit about, and this has been an environmental concern for some time, and that is lead in the environment and its effect on us as humans. And we still hear a lot about it. We hear about it especially in inner city areas, etc. We hear about it where schools were using water coolers that had lead soldered pipes. There's lead levels. Lead-based paints on old homes. Again, as I say, the inner city, which probably had wooden homes that were painted 25, 30 years ago. And at that time, and I think I mentioned this one day when we were talking about lead compounds, but lead chromate was used as a yellow paint pigment. Lead oxide was used as a white paint pigment. And so a lot of the old paint did contain an appreciable amount of lead. Well, that lead flakes off. Youngsters crawling around the ground pick up and eat little chunks of paint, etc. Or in the old days when we had the old wooden pencils with the yellow paint on it, most of the yellow paint on the pencils back in the 50s and 60s was lead chromate. And as youngsters sit there and chew your pencil, and of course so you were at the same time eating an appreciable amount of lead. But for most of us, the biggest amount of lead that we are exposed to probably comes from a compound called tetraethyl lead. And I've just abbreviated it TEL, and you can see written up this way, tetraethyl lead. Now, see, we've done enough organic and enough inorganic that we can probably come up with this. Lead is Pb. Ethyl is the C2H5 group. Remember from methyl, ethyl, propyl, butyl, pentyl, etc. Ethyl, C2H5. Tetraethyl lead means a lead that has then 4 of these C2H5 groups attached. Tetraethyl lead was added to gasoline to make it burn better. It increased its octane rating, and we like to have a gas around an octane of 90 or so for good burnability in normal compression automobiles. And so a lot of tetraethyl lead. Matter of fact, at one time as much as 10 grams of lead per gallon of gasoline was used to increase its burnability. And then we began worrying about air pollution and made catalytic converters. And we talked about catalytic converters in a previous chapter on reaction rates. The catalytic converter, however, we couldn't use leaded gasoline, as we call it, because the lead would react with the surface of the catalyst and coat the platinum nickel catalyst with a layer of lead, and the catalytic converter became useless. And even within 1 tank of gasoline would just about destroy a catalytic converter. 1 tank of leaded gasoline in a car with a catalytic converter, the catalytic converter was shot, thus defeating its purpose of decreasing air pollution. Well, anyway, so this was a major source. We've greatly decreased it in recent years, down to the point now that it's down to about 1/10 of a gram per gallon for even that gas that's called leaded gas. Most of the unleaded gas, then, they have to add other chemicals, but they're usually organic chemicals, not a lead chemical, add other chemicals to change the burnability or the octane rating. We still have to add. A lot of people said, why is unleaded gasoline more expensive than leaded gasoline when it first came out? They said, well, if we don't have to put this in, then that should make it cheaper. But the fact is, if we didn't put this in, we had to put in an organic compound to increase the burnability. And in most cases, that additive was more expensive than the tetraethyl lead. Well, the lead here, we see that air is one of the major parts. Diet, a fair amount, but diet, 90% of what we eat in lead is eliminated. 60% of what we breathe in is eliminated, but notice that 40% is absorbed. So the absorption rate through the lung for lead is much greater than the absorption rate through the digestive system. So breathing airborne lead particles from the tetraethyl lead in gasoline was quite large. We see here the 3 locations that most of it occurs, some of it in bones. Notice that there, matter of fact, 94% of it ends up in the bones. 10 to the 4th days. That's quite some length of time before the body can eliminate it. In blood, about a month. And in the soft tissue, about a month also. So we see that there, and of course they're only carrying a small amount, they're eliminated by the body, but most of it here sticks around for quite some time. Now, where the lead comes into play is in this biological system, and where we produce now the heme. the red blood cell necessary to carry the oxygen. This is where lead became a problem. In other words, lead poisoning usually showed up initially as anemia in children, and then of course it could go on and cause more severe problems as it went. The first step here is the ALA synthetase. Now, any place in biological systems we see ASE. We mentioned this in the chapter on chemical reaction rates and catalysts. Remember, enzymes, biological catalysts, always end in ASE. So every place that you see an ASE on that cycle means that an enzyme in the body has to cause that step to occur. So we have, as I mentioned, we probably have 1,000 or more enzymes in our body for specific functions. Well, in this case, we're going to synthesize this new enzyme, and lead can possibly interfere with that. If lead interferes with it, then this acid, the aminolevulinic acid, or ALA, can't be processed in the next step. Here the lead is definitely going to interfere, deactivates this dehydrase, that's another enzyme, and so this dehydrase can't be formed, and so all of the ALA comes out as waste. As a matter of fact, that's one of the ways we look for lead poisoning, is to look for elevated ALA levels in the blood tissue, in the blood fluid rather. All right, if it does make the first step, if the lead didn't bother with this, it comes around, and again you see several ACEs in here as different steps go on. We go up to here, however, and here's where we have another major problem, and that is in the final incorporation of the iron 2 into the protein structure. So this into the heme structure. Ferroketolase, that's the enzyme necessary to put the iron 2 into the heme structure, and this is where lead interferes. So lead will cut that process off, means that we can't produce heme, and therefore we also end up with our feedback, which tells the body that it should speed this up, but the lead is interfering with it, so we just keep getting higher and higher elevations of ALA in the system. So lead then, its major effect is in affecting the blood, and this shows what kind of things we can have. 10 to 15 micrograms per deciliter, that's micrograms of lead per deciliter of blood fluid. Deciliter, that's a tenth of a liter, 100 milliliters would be another way of saying it. 10 to 15, we then see the ALAD being inhibited. That was that first synthesis process. Okay, so then ALA begins to show up. Increased ALA in the urine begins to show up at about 40, and that's our first evidence of biological problems, anemia. 40 to 50, we get some peripheral neuropathy, so we start getting some problems with eyesight, narrowing of field of eyesight. We then get some cognitive effects, 50 to 60. Now, one of the problems, keep in mind, lead stays in there 10 to the 4th days. So it's there a long time. And if you're constantly exposed to lead, the body can't get rid of it. It takes a long time to get rid of it. So even though it might be a fairly low level you're exposed to, if you're exposed to that low level for a long, long time, you may actually reach these levels. Okay? We go on up, and finally when it gets to 80 to 100, we have usually acute renal injury, which means blindness, and at that point even death can occur. So there's still an appreciable number of cases of lead poisoning, even though at this point we have greatly decreased the amount of lead in the atmosphere due to gas. In our next lecture then, we will begin our discussion of oxidation reduction reactions, chapter 13.